Alright, so the proof we have here claims that the set of rational number is a countable set, and the set of real numbers is uncountable. Recall that a set A is countable if there is a one-to-one correspondence between the natural number and the given set. And if not, we say the set is uncountable. So intuitively speaking, to have a one-to-one correspondence means that we can map a function f from the natural number to a given set that is bijective, or oftentimes called one-to-one and onto. So what this means is that we have a natural number that goes from that 1, 2, 3, 4, 5, 6, 7, and so on. And we have a function that somehow maps the natural number to A in a way that it is one-to-one and onto. Like this. Well, loosely speaking, we say that a set is countable if we can list the elements off, such as the natural numbers. We can list the elements 1, 2, 3, 4, 5, and so on and so on. Or the set of integers, what about that? That a set of integers we can list off by going like this: 0, -1, 1, -2, 2, -3, 3, and so on. So we're just manipulating the way we can list them off. And then if we can list them off in this manner, then we say that a set is countable, although that is not the exact definition of a countable set. All right, what about the formal proof? How do we prove that this set of rational numbers is countable? So we'll start off with one. So we want to find a function that maps the natural number to the rational number in a way that it is bijective. The trick is to do some way like this. Let a1 just be 0. And for n greater than or equal to 2, let an be plus minus p over q, where p and q are natural numbers in the lowest terms, such that p plus q is equal to n. So what does this mean? So for example, a2 is going to look like this. It's going to be 1 over 1 and -1 over 1. Since if we add the denominator and the numerator, it's going to be equal to the n. And these are all in the lowest terms, meaning that we cannot simplify them further. What about a3? a3 is going to look like 2 over 1, -2 over 1, 1 over 2, -1 over 2. What about a4? Something like 1 over 3, -1 over 3, 3 over 1, -3 over 1. What about a5? And we'll stop at a5. 1 over 4, -1 over 4, 4 over 1, -4 over 1, 2 over 3, -2 over 3, 3 over 2, -3 over 2. What else we got? I think that's it. All right. So notice that each an is disjoint, meaning that they don't have any elements that overlap. And each rational number appears exactly once in one of these sets. So that's it. If we just consecutively line the elements of A1, A2, A3, and so on in a line, then we just found a one-to-one correspondence from the natural number to the rational numbers. So it would look something like this. We have a natural number that goes 1, 2, 3, 4, 5, 6, 7, and 8. And then we'll call this mapping function f. And then we can map onto a, an. So we'll start off with 0 because that's a1. And then a2, 1 over 1, and negative 1 over 1, that's going to be a2. And 2 over 1, negative 2 over 1, 1 over 2, negative 1 over 2. That's going to be a3. And see, we can do this for all of the an's. And we just found a one-to-one correspondence between the natural numbers and the set of rational numbers. Hence, Q is countable. All right. Oh, we're not done with the proof, actually. So that's the first part of the proof. We just showed that the rational numbers is countable. What about the second part, that the real numbers is uncountable? Well, it turns out that the real numbers is a larger infinity than the rational numbers. Although they're both infinite sets, we consider R to be large than Q in terms of cardinality. So how do we prove that the set of real numbers is uncountable? We're actually going to be using proof by contradiction. So assume for contradiction that R is countable. We're going to assume that R is countable and somehow form a contradiction. Since R is countable, we can list out the elements like we did for the natural numbers. So say R is a set, and we can enumerate each element like this. All right. Now the trick is to construct a nested interval and invoke the nested interval property to get a contradiction. So the idea is this. Here's a visualization. We're going to have our first interval, I1, that does not contain x1. And we're going to have the second interval that is entirely contained in the first interval, which does not contain x2. And then we're going to do that same for all the intervals that are inside. All right. So let I1 be a closed interval such that x1 is not in I1. And just for clarification, these x1, x2, x3 are the elements of the list of the real numbers we have up here. All right. Now let I2 be a closed interval that is entirely contained in I1 such that x2 is not in I2. Do you see the pattern here? In general, given the nth interval, construct in plus 1 such that 1 in plus 1 is entirely contained in I1, and 2 xn plus 1 is not in in plus 1. All right. Now, let xn not be some element in the list of R. So the list of R's is referring to this list of R. All right, so we're going to let xn not be any element in that list. Well, we know that xn not is not in in not, right? From our construction of the nested intervals, this is true, and this implies that xn not is not in the infinite intersection of the closed intervals. Since xn naught is not going to be in one of the closed intervals, obviously xn naught is not going to be contained in the infinite intersection of all these intervals. All right. So we're seeing that since we made x and naught be arbitrary, we're seeing that every real number, every number that is in the list of real numbers is not in the intersection of the infinite intersection of the closed intervals. Well, now here comes the punchline. However, nested interval property asserts that there exists at least one element, let's say x, that is in the infinite intersection of our closed interval. But we saw that all of these elements in the real number, in this list, is not in the intersection of the infinite intersection. So there must be so that means x must be a number that is outside the list of R. Well, that's a contradiction since R contains every real number. And thus such enumeration of R, and this enumeration refers to listing off all of the elements in this way. So we see that the contradiction concludes us to saying that such enumeration of R is impossible. We can't just list out the real numbers like this, like we did for the natural numbers, because they far outnumber the natural numbers. Hence, R is uncountable. And that's the end of our proof. So we showed that the set of rational numbers is countable and the set of real numbers is uncountable.